Hi, and welcome back. We're going to be doing averaging and data inspection. This is the last of our pre-processing steps. We have done filtering all the way up through artifact rejection. Now we are just going to be working on averaging our data. So why do we do this? Well, individual ERP trials are pretty noisy, and our ERPs are embedded in this larger EEG signal. However, the target neural signal is relatively small compared to the large background activity, and we need to minimize the noise that's in our data to pull out that small activity. We basically are trying to increase the signal to noise ratio. We do this through signal averaging. It's simple arithmetic. It's a mean of our voltages across time. We have these EEG segments that are time locked to an event, and we can average across them to basically pull out the consistent features while we're also reducing or attenuating how much those varying features are seen in our ERP waveform. We're able to do this because our experiments are set up in sets of trials, usually different conditions. In fact, we want to compare across different conditions. So for example, the pizza was too hot to eat. The pizza was too hot to cry. Eat is a related word to the sentence. Cry is an unrelated word. Those might be our two conditions, and we might have many trials of those different types of sentences, our two different conditions. Those are embedded in our EEG, but they are marked. We have those triggers, our marks, where we can pull out those epochs, those windows where we have that particular stimulus. Because they are marked, we can then create an average of like kinds of trials. So we have our related words that we average together, and then we have our unrelated words that we can then average together. This allows us to pull out the common waveforms across those different trials and compare them to each other, in this case, showing an N400 to those unrelated words. One thing that people often want to know is, well, how many trials do I need in order to create an average? This is going to vary. It depends on how much background noise you have relative to the size of the neural component. If you have a larger component, you're not going to need as many trials. So for example, the P300, you might only really need 30 to 40 good trials. For a smaller component, say the P1 or the N1, because it's smaller, you're going to need more trials. You might need more like 80 to 100 trials. So it really is dependent on what component you're looking at and how noisy your background noise is. Even if you're looking at a big component, if there's a lot of background noise, you'll need more trials. The problem is you don't just want to increase the number of trials forever, right? You will eventually run into a situation where you have an experiment that's too long and somebody's going to get tired. So yes, you want good data, but you have to understand there's a trade-off between improving your signal to noise ratio and your fatigue or time to complete the experiment. One thing I see a lot of new researchers, easy novice mistake, is to be really excited about an experiment and include many different conditions, 16 different conditions, but to get enough trials for each and every condition, if you needed, say, 50 trials for each condition, that's going to create an experiment that is extremely long, and their participants are not going to give them good data after the first 20 or 30 minutes. So you have to really be careful of, do I have enough trials? And if I don't have enough trials, do I have too many conditions? I might need to reduce the number of conditions I have in order to have enough trials of each kind. So that's just something to keep in mind. When you create an average, it allows you to visually inspect the data and look to see, is this good data? And you're going to be looking for things like, is my component of interest in my data? So in this case, I might be looking to see, well, is there an N100 here? There seems to be one in, almost all the electrodes. And, maybe I'm interested in an N400, and so I might look at CZ, and it looks like there is some kind of difference between the black line and the red line right around where I should hope I would see it in CZ if I were looking for an N400. When we're doing this visual inspection, we are also thinking about reasons we might reject or reprocess our data set. So for example, if the data is really noisy, it might be because there's not enough trials in our bins or conditions. And this might be due to task performance. Maybe, participants are just not having enough correct trials. So we might have a criteria by which we say, okay, if you're not getting, more than 50% correct, we're going to eliminate you. Or if we're losing more than 10% of trials, we're going to eliminate you. We also want to make sure our data quality is good, that we have an equal number of trials across our bins or expected number of trials in specific bins. So for example, if you have 50 face trials and 50 car trials, is that what I'm actually seeing? Or am I getting, 10 face trials and 50 car trials? If so, that would be something that's an issue. And so you want to make sure they're appropriate. Or if we're doing P300 data and we have 20 rare trials and 80 frequent trials, are we getting roughly about those proportions? Even if they're not exact, right? You're going to lose some trials, but you want to make sure that the proportion is roughly what you'd anticipate and that there are enough of them. You're also looking for these bigger data quality issues. Are there large artifacts that remain in the data after pre-processing, or is there still a bad channel? And so sometimes, and I'm just going to flip back for a second, you might see there's, not in this particular data, but there's a big eye blink, for example, that you can see across all your electrodes. If that's the case, you might want to go back and reprocess your data to try and get rid of those artifacts. Or if it's really noisy still at this stage, and you can tell it's really noisy because it's still really jittery waveforms, right? You might say, oh, I might not have enough trials. Look back how many you have. And if it isn't enough, you might say, oh, I need to relax my criteria when I'm doing my artifact rejection because I need more trials. It still might be bad data. You still might have to reject them, but these might be reasons you look at it and then say, I need to reprocess. I need to go back and redo it. Once we are satisfied with our individual averages, we're going to then move on to create a grand average waveform. This is an average of all our individual participants' ERPs, and we're making a group average. This is where we can start to look at those group differences. Are there differences between our different conditions? So we'll often be looking at this grand average waveform to see, are there actually differences between our waveforms? Why do we create them? Well, first of all, our individual ERP waveforms vary quite a bit just due to individual differences. So a grand average waveform is doing the same thing that an individual average is doing. It's reducing some things and increasing others. In this case, it's emphasizing the pattern that are shared across participant data sets, and it's minimizing the individual differences, where the individual average is getting rid of the noise. Here we're getting rid of the individual differences, not necessarily getting rid of, but at least reducing. The nice thing about them is individual average waveforms vary, but the grand average of any 10 participants is usually fairly similar to any other 10 participants. So if I were to look at participants 1 through 10, and those are their individual averages here in this graph, and on the right-hand side, that's 11 through 20, their individual averages. If I create an average of 1 through 10, and an average of 11 through 20, and I plot those against each other, they're actually going to look pretty similar. And that's what's in the graph on the bottom there. They're not going to be, exactly alike, but they are going to be much more similar than the individuals are to each other. When we pull up our grand average, we want to inspect them just like we would the individual averages. But this time we're now saying, do our individual data sets generally look like they would match what we're getting in the grand average, right? And so we want to make sure that it's reflecting the patterns that we see in our individual data sets. And we care about this because while we expect some variability in the waveform latency and amplitude across different participants, we want to confirm that that waveform is not driven by just a few participants. This is something kind of as a critical nuance here. So yes, there'll be individual differences. Having a couple participants that just don't look the same, but they're not influencing our grand average all that much, we're not going to do anything about those. We're talking about, say you have 30 participants, 2 of them are really, really different than everybody else. And it looks like our grand average looks more like those 2 participants versus the other 28. Then we have an issue that we might need to deal with. And so you just want to make sure that that's not happening, that our grand average isn't being unduly influenced by just a participant or 2 and looks much, more like that than what it should look like if given all of the other averages. So that's just something to keep in mind. We do use the grand average when we're thinking about data quantification, but just for the purposes of looking at where might we have our time window for that data quantification. We're not going to be actually pulling numbers from the grand average. That we're going to do from our individual averages. But when we do a grand average, we're combining all the correct trials of all the conditions, really, just because we want to establish a timeline for the window of the component of interest. We're doing this time window not for each individual condition because we aren't trying to predict condition differences. We don't want to look at this and say, oh, condition A and condition B are much different in this time window versus that time window. That would be basically playing into our hypothesis and biasing what we're doing. Instead, we're looking at the overall grand average waveform aside from conditions and saying, where is the component? And then picking our window based on that component. You should not just be using looking at the component to choose your window for analysis. You should also be looking at previous literature. There are also some computational methods you could use to do this as well. But this is one part of that, is looking at your grand average waveform and looking to see what window encompasses the component of interest, because you're going to need that window to extract amplitudes and latencies and so forth when we get to quantification. The other place you see grand averages used is in communicating research findings. So you'll see in papers when they are presenting their waveforms, they are presenting grand averages, and that's to allow you to visualize the condition differences. So I'm going to go ahead and switch my share at this point so that I can show you how we do this in our program. So I'm going to, again, pretend as though I just opened MATLAB and I have to go ahead and set my path. Again, you may not have to do this step, but for those of you who do, it's kind of a nice reminder that, yes, you need to go ahead and set that path so it can find EEG Lab. And then I'm going to go ahead and open EEG Lab. Right. And so I don't want to have to go through every single step again. So in this time, I'm going to go ahead and open up another ERP data set. This is a data set, not a raw data. So I'm going to load an existing data set. And I'm going to go ahead and load subject number 1001. This is one that has already had everything done to it up through artifact rejection. And so I can see in my title 101 filtered, it's been re-referenced, I've created an e-list, et cetera, right? So this is already artifact rejected. And it's right here. It has some other things that I happen to have done to this one. And then the next thing we're going to do before we can actually average our data, in previous videos, I've gone right to averaging as the next step. But really what you want to do when you're properly averaging your data is you want to take your artifact detection and you want to synchronize it to your actual average. And what I'm doing basically is I'm saying I set a bunch of artifact flags. I said, these are the trials that have artifacts in that last data set. Now I want to say, make sure when you're doing this average that those are synced up with the data so that I know when I'm doing the average that it's just taking the trials that I said were good and it's rejecting the ones that I've marked. So I'm going to update the event list in EEG list to mark any epochs that were marked in either the original event list or in what's called EEG.reject. And I'm going to go ahead and click OK. It's going to ask me to name it. It's going to add on new stuff to the end. That's great. That's fine. You might want to save this to the desktop somewhere. That's great. Or, your computer somewhere. Go ahead and do that. I'm not going to do that for today. Then I can go ahead and create an average of my ERPs. I'm now on data set 2 that I've just kind of synced up the data. I'm going to exclude all the epochs marked during artifact detection. I'm going to leave all the rest of these as default. That's fine. I'm going to go ahead and run that. And then I have to name it. So I'm going to give it a name, just my subject number and an average. I could also save this to my computer or desktop somewhere by clicking Save ERP As, browsing, going wherever it is I want to put it and saving it there. I'm not going to do that for now, but I'm just going to create my new ERP set. Click OK. Now, up till this point, we've been saving things as data sets. This now is called an ERP set, and that's because up till now, all of our data has been either the long EEG or it's been trial, right? It's a long string. This now is an average across all of those segments, right? So we pulled them together. It's an average of just a time window. This is now called an ERP set, and it falls under the menu ERP sets. We can then plot it to do our visual inspection. When we plot it, there's a couple things to be aware of. First of all, you may or may not want to have all of your bins, all your trial types. I'm actually only going to look at the correct trials because oftentimes in the incorrect trials, there just aren't very many of them. And so it's really, really noisy. And it's not really what I'm going to be looking at anyway. So I'm going to go ahead and just click the correct ones. I might not want to choose all my channels. I could select specific ones. In this particular case, however, I do want to look at all of my trials, or not all of my trials, all of my channels, because I want to look for any noisy data or bad channels or, kind of overall impression. The other thing you want to pay attention is what is the Y scale? So, you're doing the time range, the full epoch, but if you click on auto Y scale, sometimes this number is, or these numbers are not going to be good for looking at the data. In this case, -139 is absolutely not what I want. Probably driven by an eye that's got a blink in it. So I'm going to go ahead and change that to -25. If you need just kind of a common range to use, -25 to 25 tends to work, -15 to 15-ish, something like that. Tends to work for most people. I usually do -25 to 25. I'm going to go ahead and leave the 8 just because that's what the automated was. So I know nobody went above that. And so that should work. It will automatically set the frame at 6 and 6. But if you were only doing 1 or 2 channels, you would want to change this so that you could look at them in a bigger size. I'm going to go ahead and click plot. And it's going to pull up all of my electrodes. Take a second to get through them all. And as it's pulling up, you might notice my mastoids are pretty flat, which they should be. They're a comparison, right? Then you'll also notice when it comes up that my eyes aren't perfectly straight. And in fact, as I mentioned, when I hit plot, I knew something might be going on. There was probably a blink. And that's with my vertical eye one, it's going way out of range. That's what's probably driving that. So if I were looking at this, I'm looking to see, are these waveforms generally looking okay? They are. Is the component I'm interested in there? In this case, I'm interested in the N400, so I might look at CZ or CPZ and say, is there something going on? That's CZ. There's something going on there. CPZ. I'm not seeing it any. Oh, there we are. So there's some stuff going on there. I might have chosen a little bit smaller range to see this a little bit bigger, but there are waveforms there. And that's really all I care about. Are there bad channels? Are there waveforms there? Is it looking really, really noisy? It all looks okay to me. So that is how we do an individual average. We also want to do a grand average. So I'm going to actually upload 10 more files so that we can actually look at those. Once we've created an average file, we are now not going to be loading a data set, but we're going to be loading an ERP set. So this is different, right? So we've been loading either a raw file or a data set. This is an ERP set, and that's because it's already been averaged. I'm going to go ahead and navigate to where my files happen to be. And these, you can load all of them at once. You can do this with most loads. You can load a lot of raw files, or you can load a lot of data sets as well. But I'm going to load 10 up at once. Go ahead and open those. And now these will all show up under my ERP sets. So I had just this one I created. Now I've got 2 through 11. And actually, I'm not going to use this first one I just created because I happen to load the same one. So I don't want to include it twice. But you're going to be using these ones in your grand average. So we were using compute average ERPs to create an individual average. Now we're going to be using average across ERP sets, or grand average. When we pull this up, it's going to say which ERP sets in the ERP menu do you want to use. It kindly just grabbed 2 through 11 for me. I might have needed to reset this, and it might only have one listed, and you might have to put all of them down there that you want. You can also do it in other ways, pulling from a set of files. I like to preload them and do it this way because then I can ensure I have the ones I want. We want to exclude any, that are not good, but if we leave the defaults, they're pretty much good as is. We're going to go ahead and hit run. And now I'm going to call this my N400 grand average. And again, you can save this somewhere else on your computer so you can load it later. Absolutely go ahead and do that. I'm not going to do that for right this moment, but we're just going to create the new data set. And that will appear here. So now it's another ERP set. So this is a grand average of these 2 through 11. So I can then look at this grand average just the same way I plotted my average. I can go ahead and plot. I don't know what it'll do with it. The auto scale, it's still got really pretty low. So I'm going to say -15 to 15. I'm still going to have just bins 1 and 2. I'm going to show all the electrode channels, but if I were reporting this, I probably wouldn't want to report all of the electrode channels. I would have just a couple, but I'm just going to plot all of them for now, just so you can see the difference. So now you can see it's smoother because this is now an average of our different participants. So that's really all I wanted to get through for today. We've gotten through pre-processing. And so that's the pre-processing steps. The next thing you would do is actually quantify your data. All right, see you later.